We are all familiar with the problem. It never seems like we can get a processor to run fast enough for our required application. Today, we would like to describe how one goes about acquiring data and then quickly process the data with the Zynq 7000 all-programmable SoC. At the highest level, most software designs are the same. They input some data, process the data, and then provide a set of results. For many designers, they must accomplish these tasks in a fixed amount of time. They need to quickly acquire the data, pass it via a low latency path to the processor, and process the data meeting system-level time constraints. Frequently, the data processing algorithm is simply not fast enough to meet the system requirements, and the software designer is forced to find an alternative means to accelerate their software. We have seen that ASSPs typically lack the flexibility or capabilities to address some of these performance challenges. ASSPs can become compute bottlenecks. We have all seen it before. Budget is limited, and we find ourselves having to purchase a processor that we think has the throughput, latency, and performance to do the job. This leaves us vulnerable, as we may find out too late that there is simply not enough processing power available, forcing us to optimize software at the cost of project schedule. ASSPs can be data movement challenged. Data movement is all about throughput, latency, and performance. Some ASSPs don't have DMA engines. Others have them, but the performance is insufficient. ASSPs may be ineffective in enabling quick access to real-time data. Such ASSP DMA engines are simply not set up to move data to and from locations where you really need the data, such as directly to the cache. In this session, we will address the common questions of how can I acquire data either through an external interface or via the Zynq XADC and quickly pass this data to the ARM processor in Zynq. How can I accelerate software DSP functions? Can I do it with the Neon instructions, which are single instruction multi-data? Can I go even faster by offloading software functions to programmable logic? And finally, how can I move data via DMA between the programmable logic and the processing system to accomplish the above tasks? We have put together a Zynq 7000 all-programmable SoC design example helping to answer these design challenges. By integrating a processing system tightly coupled to the programmable logic, one can break the compute bottleneck with software acceleration. This design shows how a fast Fourier transform can process the data with software, and then how the same FFT can be performed using the integrated Neon instruction set. The Neon instructions are single instruction, multi-data, and in this example, enable the floating point FFT to be processed 45% faster. Even higher performance can be obtained with integer vector instructions, where 4 or 8 integers may be processed in parallel. For even greater acceleration, the design demonstrates how the FFT may be processed via a hardware accelerator located in the programmable logic, showing 6.4 times acceleration compared to the software FFT. To accomplish such acceleration functions, it is critical to move data quickly with data movers. This design shows how data may be moved efficiently to and from the processing system and programmable logic via DMA engines, including how to configure, connect, and manage the DMA engines. Finally, for real-time applications, it is important to obtain low-latency access to real-time data. We demonstrate how one can acquire 12-bit analog-to-digital data via the integrated XADC at 1 megasample per second and pass this data directly to the processor cache via a data mover. We have packaged the design as a ready-to-run demo and 5 design examples, including source code, which is available on our wiki at wiki.xilinx.com. To accelerate our implementation of the design example, we started with the targeted reference design that is provided at no additional charge with the Zynq 7000 All-Programmable SoC ZC702 Evaluation Kit. This reference design includes an integrated software and hardware design demonstrating streaming video processing. We use the same Linux kernel as provided without rebuilding, the video display pipeline, the example graphical user interface, and software application as a starting point. To this design, we add a DMA engine to acquire the ADC data and pass it via the accelerator coherency port, or ACP, interface into the L2 cache. We use the Xilinx Logic Core FFT to implement the 4096-point FFT engine and attach it via a DMA engine to move the source data and FFT results to and from the processor via the ACP to the L2 cache. To summarize the results, when using software alone, the 4096 complex 32-bit floating point FFT is completed in 830 microseconds. When using the Neon SIMD engine integrated into the ARM processor, the time drops to 570 microseconds, which is 45% faster. And when the processing is offloaded to the programmable logic, the task is completed in 129 microseconds, which is 6.4 times faster. This is as if the 667 megahertz processor is processing the data at the rate of a 4.3 gigahertz processor. Now let's check out our demonstration. For the demo, the setup is really quite simple. Download and program the SD card with the Spectrum Analyzer demo and install the SD card. Set the boot configuration dip switch to boot from the SD card. Connect a mouse to the USB, on-the-go interface, and a 1080p monitor to the HDMI interface. And optionally, connect your phone or MP3 player to the optional audio to AMS adapter. Then turn on the board. We're now looking at our live demonstration of the FFT signal processing. In the upper window, you have the audio input signal, which is now being sampled at 100,000 samples per second. In the lower window, we have our 4096-point FFT being displayed. You have options for this particular demonstration. You can select whether or not you want to have your external test pattern generator, which comes standard. The test pattern generator generates 2 amplitude modulated signals on top of an FM modulated signal. You can zoom in, as we're currently doing, by 5 times on the FFT display. You can select your FFT scale, and you can select the type of FFT window that you want to have. Currently, we're doing a software-only FFT. If you look down here in the lower left-hand corner, you'll see that the time to compute that FFT is roughly 800 microseconds. So this is software only. I'm now going to switch it to computing using the Neon instruction set. And you'll see that that 800 microseconds now goes down to about 550 microseconds. This is our 45% acceleration that I mentioned earlier. And then finally, I will select the programmable logic accelerated. And looking down again in the lower left-hand corner, you'll see that the time to compute that FFT is 130 microseconds. This is our 6.4 times acceleration of the software. I've had the audio turned down for this demonstration so that you can hear me, but let me go ahead and turn on the audio and so you can see how the audio waveform is processed and displayed in the FFT.
Changed your life when you walk into an audio video store. It's really mind-boggling.
To summarize, The Zynq 7000 all-programmable SoC with its tightly coupled processing system offers capabilities not found with off-the-shelf ASSPs. The ability to relieve your software bottlenecks by the use of neon instructions for arithmetic acceleration and via programmable logic accelerators for even higher performance. The capability of implementing application-specific data movers in the programmable logic capable of moving data quickly within the programmable logic, between the programmable logic and the processing system, and between the programmable logic and memory. And finally, with such a system, one can obtain low latency access to real-time data via data movers and direct access between the processing system and programmable logic via Xilinx DMA engines. For additional information, please visit the following websites. Thank you.